Good morning. We are going to look today at the third unit of the fourth module dedicated to work and power. This unit is about conservative and non-conservative forces, and here we have the index that we are going to continue talking about what are conservative, what are non-conservative, and their relation with closed trajectories. This topic is going to be on the one hand quite descriptive. We are going to give definitions, but we will also take the opportunity to give some examples that will use the formulas that we have been looking at in the previous units. The first thing is the definition of what a conservative force is. The definition is that it is one whose work between any 2 points does not depend on the trajectory. For example, there we have some points A and B. We can calculate the work along this path, APB. We can calculate the work along this other path, AQB, and along this other more twisted one, ARB, and discover that the three works are exactly the same, that the path has not influenced, and we can have taken any other trajectory of those not represented here, as long as it goes from A to B. If we go from A to another point C, different results will be obtained. That is to say, I am not saying that all the works are equal, only that any work between any point A and any point B is indifferent to the trajectory, therefore only depends on the ends of the trajectory, not the path between them. It is not a general case when that property is given that says that it is a conservative force. Let's see examples of these cases. The first and most famous is the constant force. Why a constant force does not depend on the path? Well, we already know in the particular formula, when the force is constant in modulus of direction and sense, the work is, as we saw in the previous unit, the scalar product of the force by the vector that joins point A and point B. Obviously, this equation does not depend at all on the particular path. If I go along another path with the same F, the same origin A, the same NB, I get exactly the same result. So any constant force is conservative. Another slightly more sophisticated example, the uniform gravitational field. Actually, it is a particular case of the previous one, but let's take the opportunity to see some examples a little more sophisticated. I am talking about the terrestrial field understood as being mass by the acceleration of gravity. Therefore, we are not taking into account that as we move away from the surface of the Earth, that force, that weight is changing. Here we have several trajectories that we are going to follow. We are going to go from point A to point B by three paths, the APB, the AQB, and the ARB. And one parameter that we are going to need is precisely the height, the difference in level between the starting point A and the end point B. Let's start with the APB trajectory. Recall that I can decompose a trajectory into parts and get the total work as the sum of the partial works, as we saw in the first unit. We start with the section AP. In the AP section, the force is all the time the same. M vector G does not change. And it is a particular case of constant force on a straight path that has the same direction and sense as the path that the displacement is, therefore, the particular case that appears on the screen that we see as simulated above on the left. Therefore, the corresponding formula is modulus of the force, in this case mg without arrow above, by the displacement, which in this case is h, as we have here put, where it says trajectory AB. We put that the work is mgh. The next section would be the PB. In the section PB, we see that the force is at all times, the weight is at all times perpendicular to the trajectory, therefore it corresponds to the particular case that is being shown now. In that case, as we know, the work is zero, so I'm left with balance. As we see here, mgh plus 0 equals mgh. That's the work that the weight has done on the APB path. In the AQB leg is quite similar. The difference is that in the first leg, the AQ, the force is perpendicular to the displacement, and therefore the work is zero, as it was in the PB. And the section QB, it is analogous to AP. The force is constant, parallel to the movement, rectilinear and of the same direction. Therefore, it is the modulus of the force, mg times the distance traveled h. The sum is again, as we can see here, mgh. As a third example, the trajectory ARB corresponds to this particular case now shown. It is a force of constant modulus that forms an angle that is oblique with respect to a rectilinear trajectory. In that case, if we recall, the work was the tangent force times d. the tangent force. We can calculate it as a function of the angle that the weight forms with the trajectory. That angle we have called phi, and it is by trigonometry mg, modulus of the force by cosine of that angle. Well, rearranging terms by the associative property, I am left with mg for the distance AB cosine of phi. Well, since this angle is also the same as this one, it's also phi. We have triangle APB, of which d sub AB is the hypotenuse. Here we have the angle, and d cosine is precisely this distance. That is to say, d cosine in this case is precisely h. So for the third time, it has given us the same result. We can do more complicated cases with curved trajectories of the strangest form that we can imagine, but for that we would have to know how to handle the generic integral that we have said, that we would not need to use. That yes, it would give mog again, always in all cases. So, well, the uniform gravitational field is a conservative force. What is a non-conservative force? That which is not conservative, that which does not fulfill the property of being conservative. Its work between any 2 points depends in general on the trajectory. I say in general because it may happen that for a particular pair of points, I get all the time the same for any trajectory, but remember that to be conservative, it must be that with any pair of points, whichever always gives me the same result. If there is an exception, it is no longer conservative. Therefore, I repeat, one exception is enough for me. So well, if it depends in general, not necessarily always on the trajectory, or in this case in which the three works are different, the force by definition is non-conservative. Obviously, forces are one thing or the other, there is no third category. Examples. The frictional force is the quintessential example of a non-conservative force. For example, we are going to go from point A to point B, and we are going to imagine that we have a frictional force that always goes against the movement, against the displacement. And we are going to suppose, to simplify in this case, that it is of constant modulus, so that we see how it influences. There we have first what would happen if we went from A to B in a straight line. On the particle would act a friction force F sub r that would go all the time in the opposite direction. It would be the case that we are seeing up there, the path of any shape, in this case straight, but well, it can be any shape. With that force is all the time of the same constant modulus in the sense against the displacement. In that case, the work is less F by length of trajectory curve, remember. In this case, the trajectory APB measures twice the radius. However, if we go for the part of the arc of circumference of semicircle AQB, we have the same case. It's still the same particular case. The frictional force has the same value. It still goes against, but the length of the curve AQB is half of a circumference, half of 2 times pi r. That is pi r. Obviously, if the work for the first trajectory is minus fr times 2r, and the second minus fr times PIR, then the result is not the same. Therefore, we have been influenced by the trajectory, and with other trajectories that we can try, it would be even more noticeable. The frictional force, therefore, is not conservative. The trajectory, in particular, influences the result. Let's look at another example, which is the force exerted by a current. Let's imagine that we have a river through which water flows, and that the speed depends on the depth. The closer to the bottom, the water goes slower. The closer to the surface, the water goes faster and exerts a greater force, a pattern of forces like the one we see there. And let's see what work that force does on a particle going from AB in a straight line, or going from AB, describing an U, that will pass through points Q and R. Here we're calling B the distance between points A and B, and this value will appear to us next. First of all, if we go along the direct path APB, what we have is the particular case already analyzed before or already known before, which is that we have to multiply simply, for being of the same direction and sense in rectilinear trajectory, the modulus of the force by the distance traveled, F1 times B. If we go from A to Q, we are in the particular case of force acting perpendicular to the movement, zero work. From Q to R is force acting in the same direction as the motion, same as above, only the modulus is F2, not F1, so the work at the bottom is F2B. In the ascending part, it is again perpendicular to the trajectory, the work is zero. In balance, the trajectory A, QRB, gives me a work F2B, since F1 is larger than F2, as we see in the figure. It turns out that the work that is exerted, the force of the current is greater going in a straight line than passing through the bottom. Therefore, depending on the path, it is a non-conservative force. A quick way to recognize them many times is to analyze what they do in closed curves, in closed trajectories. We are not going to demonstrate it, but we are going to see this property. When a force is conservative, it turns out that in closed trajectories the work is zero. Whatever we do, this is always the case. In the case of a constant force, we are going to see that this is indeed the case. If I apply the formula that work is force times A, B, taking advantage of the fact that the force is a constant vector, obviously the vector A, B is zero, since it goes from point A to point B, which is point A itself. The vector that joins them is 0, 0, 0, 0, and the scalar product is 0. Effectively, we have that the work is 0 in a closed trajectory. Let's go to another example, a closed trajectory that would be going from A to A, passing through P, B, Q, traversing the rectangle. Here, we have a case already known. In fact, we have done it in the previous example, which would be MGH. Here we would have zero work at the bottom. Going back up, the work would be, particular case again, force acting in reverse. Recall that we are now going from B to Q, not as in the previous example, which we went from Q to B. Here the force acts in the opposite direction to the displacement. So the formula is minus F modulus by distance. In this case, minus mg times h. In the last section, the work is zero. So adding all this up, we can check that indeed the work on the closed curve has turned out to be zero, as corresponds to a conservative force. Let's see an example of a case where it is not conservative. When we have non-conservative forces in closed trajectories, the work in general, it is not zero. It may happen that in some particular case it is, but it is not the general case. Recall that it is enough that there is a closed trajectory that does not give zero. Well, in general, it is not. Let's look at the example of the frictional force, which is, as I say, the most common. Here we have a frictional force acting at all times in the opposite direction to the displacement. Therefore, the formula is the one we have already analyzed above, minus the mode of that friction force by the curve length. Obviously, the frictional force does not have zero modulus, the curve does not measure zero, and therefore this product is not zero. Therefore, the frictional force, once again, is not conservative. All this is summarized in this transparency. A force is conservative if its work between any 2 points does not depend on the trajectory, and moreover, has the property that its work on closed trajectories is zero. On the contrary, for non-conservative forces, we have that their work between any 2 points depends on the path followed on the particular trajectory, and the work along closed curves is, in general, non-zero. Thus we end the third unit